Hello, class. Welcome to our Combinatorics lecture for Monday, March the 30th. I want you to remember that your homework number 4, right, is due uh, this evening by midnight, and I have I have posted instructions, right, on how to submit that homework, but it's very simple. You're simply going to scan the homework, right, into a PDF file. And if you look over here in this homework folder, that does give you a little bit of instructions on if you don't know how to do this, right, how to scan a document, right, into a PDF file. Of course, you can do that with a scanner, but you can also do that easily with apps on your phone. So that may be the preferred method in this case, right? Then you're just going to email that, right, to my regular email address, right, wallerw@uhd.edu, again by midnight, March the 30th, right? So if you're watching this on Monday, March the 30th, by midnight tonight, and then that will allow me to grade those and then actually return them to you as well, graded. Your homework number 3 that I currently have, I may have that graded by the time you get to watch this. That I will not be able to return to you, but because I don't have a fast means of scanning all of those assignments so that I can email them back to you. But I will, as usual, right, post the solutions. Um, uh, or actually, the solutions are already posted, right? So I've already posted the solutions to homework number 3, and for homework number 4, after you submit that, I'll be posting the solutions for that homework as well. Notice I've posted a new homework, right, that's going to be due in the same fashion on April the 8th. And so that's posted. These are problems from the book. I've attached there at the end of this document, there's a scan there of the book pages where the homework problems are, and these problems are all about the topic that we're going to continue talking about today, which is the pigeonhole principle. Okay. Now, another thing that I wanted to mention that I know you're curious about is the next test, right? Test number 2. So again, I've sort of mentioned briefly how that's going to work, but it's going to be very similar to your homework assignments. So what's going to happen is on April the 8th in the morning before class, I'm going to post that test. Somewhere here on Blackboard, okay? I'm going to post that test, and then I will, and then you will just look at that and write out your answers, and then you will scan your answers and return them to me by Friday morning at 10 a.m. right when the class ends. So you'll have between 8:30 on Wednesday, April the 8th, and 10 a.m. on Friday, April the 10th, to write down your solutions, scan them, and email them back to me. I will be posting a sample tests. Right, in the usual way, and so that may be posted by the time, I haven't posted yet, by the time you see this lecture, though, on Monday, March the 30th, it may be posted, or it will be posted shortly after that. Okay, so be shortly after the time of this lecture, which is 8:30 on, again, Monday, March the 30th. So be watching for that, right? So there will be a sample test available. So we're going to try to continue, for the most part, doing things the way we did before the break, right? But except that you'll be taking your tests at home instead of face-to-face. Okay. So I hope everyone is doing fine. I'm okay, and so I hope y'all's life is actually boring, because if it's exciting, I think that might not be a good thing. All right, so I hope you're stuck at home and bored, and so you'll have plenty of time to work on your Combinatorics homework. Okay. All right. So I'm going to return now to our lecture, and today we're going to talk about more about the pigeonhole principle, and then about again, as I mentioned in the last lecture, a important and sort of philosophically profound generalization of the pigeonhole principle that's called Ramsay's. Well, it's Ramsay's theorem is the specific result we're going to be talking about, but Ramsay's theorem is part of a much broader topic in mathematics called Ramsay theory. But again, this is related to it's related to the pigeonhole principle. All right. Okay. So last time, so I'm switching to the notes now. So last time we had introduced the pigeonhole principle, right? So this is a very basic idea in logic, a very basic tool in logic. And so we had introduced this so-called principle in the form of a theorem, and we actually gave a proof of the theorem. And then we looked at one simple application of the pigeonhole principle. Today we're going to look at some more, a little bit more complex applications of the pigeonhole principle, right? So what the pigeonhole principle says, right, it's got a colorful title, right, because there are lots of colorful ways of restating this theorem, but the pigeonhole principle says if you've got n plus 1 objects, in here is think of n as being a positive integer here, right? If you've got n plus 1 objects, right, and you've got them distributed into only n boxes, right? So you've got more objects than you've got boxes, correct? Then at least one of the boxes will contain 2 or more objects, right? So that's a very easy piece of logical deduction, right? But it occurs frequently in proofs of theorems. In mathematical reasoning, this particular deduction occurs frequently, so it's singled out to have its own name. Again, it's called the pigeonhole principle, right? Okay, and one can actually prove this, so it really is a theorem because one can give a proof to it. All right, and then we looked at this example last time, and today we're going to look at a more fun example here, all right, or some more fun examples. All right, so let's start with the first one. I've actually got the all of this argument already written down, so I'm just going to sort of read through the argument, and on the next example, I don't have the entire argument written down, so I'll be writing that as I'm talking here. But suppose now, so in this example, suppose we have a collection of integers, okay, and I think we can assume that they're all positive integers. So suppose we have a collection of positive integers, and we've got m of them. All right, so m of these positive integers. So if we want to, we can number them, right? So there's a sub 1, a sub 2, a sub 3, etc., up to a sub n. You do not have to assume that the integers are written in numerical order. Okay, so they can be mixed up in any order that we like, right? Okay, and integers can, and some of these integers can repeat one another. So there's no requirement that the integers all be distinct, right? So you've just got a collection of m, right, positive integers. And so here's what we're going to show here. Then what we're going to show is that there's some sequence of some consecutive sequence of these positive integers that's going to be divisible by the number m, right? Remember, m is the number of the positive integers, but these positive integers can be any size, right? M is just the number of the positive integers that you have, right? Okay, so what we know is that some sequence of these, when you add them all together, then that sequence is divisible by m, okay? I should have written this as, then there is a sequence of consecutive a's, I should have said whose sum is divisible by m, okay? That might be sort of implied by the wording, but let me make that a little bit more explicit there. And let me also change my pen color here back to black. All right, so before we actually demonstrate that this is true in general, let's look at a specific example of some collection of these positive integers, and let me show you what I'm talking about. So look at this collection of positive integers, right? Okay, so 2, 4, 6, 3, 7. 2, 4, 6, 3, 5, 5, 6, right? So again, see we're not assuming that the numbers have to be written in numerical order, right? Okay, so this is mixed up a little bit, right? Not in numerical order, but what we want to what we're going to prove here, but we'll demonstrate it in this sequence. But what we're going to in this collection of integers, but what we're going to prove in general is that there's a subsequence here, right? So that when you add up the numbers in the subsequence, it's got to be divisible by 7. Which is the number of numbers in this collection, right? There's 7 numbers in this collection. All right, so it's easy to pick out in this case such a subsequence, right? Because if you take 6 and 3 and 5, right? 6 plus 3 plus 5, that subsequence, right, of those 3, right? In this case, they happen to be right in the middle of my collection, right? But that subsequence of those 3s, when you add that up, you get 14, of course, and 14 is divisible by 7, right? The number of numbers in the collection. If you look hard enough here, you might be able to find another subsequence also that is divisible by 7. Okay. Oh, no, I thought I saw one there really quickly, but I don't. All right. Okay. So, all right. So, if you want to, you can look around and see if you can find another subsequence here that's divisible by 7. It could be all of the numbers, by the way. It could be the subsequence, right? Okay. If you add up all these numbers, it's maybe that's divisible by 7. Okay. All right. So. So there's just a kind of a demonstration, right? But what we're going to show is that this fact here is not unique to this collection of numbers that I wrote down, right? This is true anytime you write down a collection of positive integers. All right, so let's see how we're going to prove this now. Okay, that this is always going to be this kind of mathematical curiosity here is always going to be the case. All right, so just in general here, again, since we're not looking at a specific example, right? Okay, we're just looking at a sequence in general, right, or a collection of numbers in general. Then let's just suppose, right, that we've got that collection of those numbers labeled, right? Okay, so one of them is a sub 1, one of them is a sub 2, up to the last one is a sub n, right? Since we're assuming we have m of the integers, all right? Now, what I'm going to do is I'm going to form what are called partial sums. And we're going to revisit this concept of partial sums because this is this plays an important role in other parts of the course, but it also plays an important role in other aspects of mathematics also, right? So for those of you who have taken Calculus 2, you might have studied partial sums already at the last part of that course when you were studying sequences in series, because they play an important role in the study of sequences in series, and we're going to use them in this sequence as well, right? So I'm going to let a sub n, I'm going to let that be the sum of the first n positive integers, right? Okay, and so you're going to create such a partial sum for every possible subscript here n up to m. All right, so for example, let's be clear what I mean. So a sub 1, capital A sub 1, that would be the partial sum that just includes a1, right, the first number in your collection. But a sub 2 then, right, capital A sub 2, that would be little a sub 1 plus little a sub 2, right? You would add up the first 2 numbers in your collection to give you capital A sub 2, right? Capital A sub 3 would be adding up the first 3 numbers in the collection and so forth, right? So a sub 4 then obviously would be a 1. Obviously, that would be a 1 plus a 2 plus a 3, right, plus a 4. So that would be the sum of the first 4 values, right, in the collection. All right, so you're going to create that partial sum again for every possible subscript here, right? So all the way up to m. So for instance, a sub m, right? That would mean the sum of all of the numbers in the collection. So that would be a1 plus a2 plus etc. all the way down to am, right? Okay. All right. So notice you're going to get several of those partial sums, right? Okay. A1, A2, A3, etc. Sorry, capital A1, capital A2, capital A3, all the way up to capital A sub m. Now, it's possible that one of those, once you form all of these partial sums, right, it's possible that one of those already is divisible by m, all right? And if that's the case, then you're in great shape, right? Okay, that means you found the collection so that when you found the subsequence, right? So that when you add them all together, you get a number divisible by m, correct? Okay, so that would be a happy situation, right? If one of your partial sums is already divisible by m, then you're done, right? Okay, again, you've got the subsequence whose sum is divisible by m. So we have to look at the situation where that happy thing does not occur, right? So we have to assume that none of these partial sums is really exactly divisible by m. All right. So what I'm going to do now is come through here, and I'm going to divide all of these partial sums by m. Again, now we're going to assume that none of them is exactly divisible by m, right? Because if one of them were, again, we would be already finished with, we would already have found what we're looking for here, right? So I'm going to divide a sub 1 by m, right? Okay, and so if this is not divisible by m, that means I have to get a remainder that's not 0, right? So let's call this remainder r sub 1, right? And what do you know about r sub 1? It cannot be 0, right? But, so it's got to be 1 or 2 or 3, right? Okay? But it cannot be m either, right? Because when you divide a number by a value, your remainder is not going to be any larger than the divisor, correct? So whatever r1 is, right? Okay? You know it's bigger than 1, right? Or bigger than or equal to 1. But at the same time, it has to be less than or equal to m minus 1. It cannot be equal to, it cannot be as large as m, right? And so I'm going to keep doing that. So I'm going to take a2. This is the second partial sum, right? And I'm going to divide that also by m. Remember, a2 is a1 plus a2, right? Okay, so I divide that by m, and that gives me that I'm assuming that's not divisible by m, right? Because otherwise I would be done. Right? And so that's going to give me a remainder also. So I'm going to keep on doing this, right? I'm going to divide a3 by m, right? Okay? And I'm going to assume that gives me some remainder that's not 0, but is not as big as m, correct? And so on and so forth, all the way out to the last partial sum. Okay. So let's call this remainder a sub r sub m, right? Okay. So again, you know that r sub m is not 0, because otherwise a sub m would divide by m, but it can't be as big as m, right? So it's got to be less than or equal to m minus 1. All right, so you go through this process, you form all of these remainders, right? And all of these remainders are between 1 and m minus 1. But how many remainders do you have here, right? Okay, well, you've got m of them. So you've got m numbers, right? All of them are between 1 and m minus 1. So think of that. I've got m numbers, but all of the numbers are between 1 and m minus 1. So by the pigeonhole principle, guess what must be the case? 2 of these remainders, I don't know which 2, right? But 2 of these remainders that I formed have to be the same. Okay, so 2 of the remainders have got to be the same. All right, okay, so interesting. All right. So if two of the remainders are the same, right, that means two of my partial sums, right, have the same remainder when I divide by m. Okay, so let's just suppose, I don't know which two these are that give me the same remainder. So let's suppose that the two partial sums are a sub j, right? I'm not sure what this subscript is, but one of the partial sums, and then the second partial sum that gives me the same remainder when I divide by m, let's call that a sub k. And one of these subscripts have to be bigger than the other. So I'm going to assume that j is smaller than. I'm going to assume here that j is smaller than k. All right. So this means that when you take, again, right, when you take the partial sum a sub j, you're adding up a1, a2, little a1, little a2, little a3, etc. up here, up to a j, right? And then when you form the partial sum ak, right, you're adding a1 plus a2 up to a sub k. All right. And these things have to have the same remainder when you divide them by m, okay? So what you know here is that a sub j is going to be something times m plus this remainder rj, right? And a sub k is going to be something times m. So here I wrote this as c times m, again, plus some remainder, right? But these two, remember, we're assuming these two remainders are the same, right? So this remainder, when you divide a sub j by m, I was calling that r sub j up here, and then this remainder, when you divide a sub k by m, I was calling that rk up here. These two remainders are the same, okay? All right. So here's what I'm going to do now. I'm going to take a sub k, and I'm going to subtract off of that. I'm going to take a sub k, and I'm going to subtract off of that aj. All right? So I'm going to take this big partial sum, and I'm going to subtract off from that aj. All right, so think about what happens now when you subtract this partial sum from this one. Remember, I'm assuming this value is k is bigger than j. All right, so let's write that down. So a sub k minus a sub j, right? So what happens when I take this larger partial sum and subtract this smaller partial sum from it? Well, notice, of course, a lot of the terms between the two partial sums are going to cancel each other, right? Because a sub k and a sub j, they both have a 1, right? They may both have a 2, right? Etc., etc. So a lot of these terms, when you subtract aj from ak, a lot of these terms are going to cancel. But some of the terms will not cancel, right? Because this partial sum has more terms in it than this one. So the terms that won't cancel will be ak, right? And then down to a sub j plus 1, right? Okay, because a sub k has all of the terms of a j in it, right? Except the terms that exceed little aj. So when you subtract this partial sum from this one, you get aj plus 1, right? Plus aj plus 2, all the way up to ak, correct? Those are the terms that don't cancel when you subtract a sub j minus a sub k. All right, so you've got this sum, but notice now we also know that we're also assuming here, right, that a sub k is something times m plus this remainder, right? This is rk, right? And then a sub j is something times m plus this remainder, r sub j, right? So, so you, of course, a sub k minus a sub j is this sequence of terms, but it's also the difference of these two quantities as well. So when you take the difference of these two quantities, since these two remainders are the same, notice they cancel each other, right? And so you just get cm, c times m minus b times m, which is c minus b times m plus 0, right? So guess what that means? That means that when you add these numbers together, aj plus 1 plus a sub j plus 2 up to a sub k, guess what? that means then that they're going to be some number times m, right? In other words, this sum is a multiple of m, or this sum is divisible by m, because when you divide by m, you won't get a remainder. So there you have it. Okay, there's the sequence, right? The subsequence, right? Embedded in your original group of numbers, there's the subsequence that has to be a multiple of m. So see, this is going to be true for any collection of integers at all. Oh, okay, all right. So, that's interesting. So, whenever I write down a collection, here I've written down a collection of integers, right? Okay, 12, 19, 21, 7, 3, 8. Remember, they don't have to be in any order, all right? So, so what I know is that some subsequence of this collection has to be divisible by 6, because there are 1, 2, 3, 4, 5, 6 numbers, right, in this collection. All right, let's see if we can identify, using that same logic in that argument. Now, you can easily just spot this. I think you can just scan through here and spot the subsequence that when you add the numbers together, you'll get something divisible by 6, right? So it's not hard for you to look at this and find such a subsequence. But let's do it using the, because this is a very short collection of numbers, right? But let's find actually that subsequence using our argument, using our logic from that argument above, so you can understand that logic a little bit better. In the argument, we were giving it symbolically, but here we can give it a little bit more concretely, right, with this example. So remember, first we're going to form the partial sums, right? So A1 would be 12, and then capital A sub 2 would be 12 plus 19, which is 31, right? And then capital A sub 3 would be 12 plus 19 plus 21, which is 12 plus 19 plus 21, which is, what's that going to be? 52, right? Okay. And then is that right? Did I do that right? 31 plus 21. 31 plus 21 is 52, right? Okay. So then A sub 4 would be 59, right? And then A sub 5 would be 62. And then A sub 6 would be 70, okay? Isn't that the sum of all the sequence? 52, 59, 62, 70, right? Okay. So next what you would do is already, oh darn it, this is not fun, is it? Okay, because what we would do here already is scan through this collection of, partial sums, right? And if one of them is divisible by, if one of them is divisible already by 6, then we would say we're done, right? Okay, oh, well, so here we already have one of our partial sums, right? 12, that's divisible by 6, correct? And so there we've already identified, right, our subsequence that's divisible by 6, okay? All right, so quickly, right, in this case, we can find that subsequence. All right, so let's alter our numbers here just slightly, okay, and so that we don't get a subsequence, so we don't get a partial sum that's divisible by 6, okay? So can we see how to do that? If I change this one to 13, if I change this first number to 13, right, then this first partial sum is not divisible by 13, right? Then the second partial sum is, what, 19 plus 13 is 32, right? So that also is not divisible by 6. The third partial sum then would be 53, right? The 13 plus 19 is 32 plus 21 would be 53, which is not divisible by 6. And then we would add 7 to that. Oops, that is divisible by 6, though, because that would be 60. So let me change this number to 8, okay? And then the fourth partial sum would be 53 plus 8, which is what, 61, right? Which is not divisible by 6, right? Okay, and then we would add 3, and that would give me 64, also not divisible by 6, right? So this partial sum not divisible by 6, and then we would add 8 to that. Well, unfortunately, 8 plus 64 is 72, which I think is divisible by 6. So let me change this last number to here to 9, which is not divisible by 6, and then which is itself not divisible by 6, right? But now when you add 9 to 64, that will give you 73, which is not divisible by 6 either, all right? So here we have a slightly different collection of numbers, but still some subsequence here has to be divisible by 6. But in this case, none of the partial sums, right? None of the partial sums themselves is going to be divisible by 6. So now we have to extend our logic from that previous. Argument, right? Okay. So all right. So now what does that logic say at this point? Since none of the partial sums is divisible by 6. Well, it says take all of your integers, right? And take all of your partial sums and divide them by 6, right? And see what your remainders are, correct? Not what the quotient is necessarily, but what is the remainder, okay? So here we have a remainder of what? 1, right? So here we get a remainder of 1, and then we take 32 and divide that by 6, and that gives us a remainder of 2, right? So then we get a remainder of 2. And now we take 53 and divide that by 6. Let's see, I think that gives us a remainder of 5 if I'm doing that properly. And then we take 61 and divide that by 6. That gives us a remainder of 1. And then we take 64 and divide that by 6. That gives us a remainder of 4. And then we take 73 and divide that by 6. And that gives us also a remainder of 1, correct? So notice now, again, as promised, right, lots of these, more than one of these, at least, right, remainders are the same. We get here 3 remainders of 1, right? But you had to have at least 2 of the remainders being the same, because you had to have 2 of the remainders being the same, right? Because you've got 6 different remainders that you're forming, but all of these remainders, if they're not 0, have to be between 1 and 5. So there's only 5 possible values that the 6 numbers could take on. So we knew that 2 of them had to be the same. So let's focus on these 2. So this is the remainder for that's the remainder, right, for a sub 1, right? And here's of course, the remainder for a sub 4, correct? Those 2 remainders are the same. So we know that a sub 1 can be written as something times m plus 1. Of course, it's going to be 2 times 6, right? Plus that remainder of 1. And a sub 4, since its remainder is 1, it's also equal to something times 6 plus 1. In this case, it's 10 times 6, right? Plus 1. So now, what happens when you take a sub 4, right, minus a sub 1? Well, that's going to be, of course, 10 times 6, right, plus 1, minus 2 times 6 plus 1, minus 2 times 6, right, plus 1. And of course, that turns out to be 8 times 6, right? So a sub 4 minus a sub 1 has to be a multiple of 6, right? Okay, is that correct? Yeah, 61 minus 13 is 48, which is 8 times 6, right? So what this means is that the sequence of a subsequence of numbers between the values that formed a sub 1 and the values that formed a sub 4, right? Okay, that subsequence has to be a multiple of 6. That is, in this collection of numbers, these numbers. Remember, you added up the first 4 to get a sub 4. Just the first number itself is a sub 1. So when you take a sub 4 minus a sub 1, you get left with these 3 values, and they have to add up to 48, 8 times 6, which is a multiple of 6. So there we found it, right? There's our 3 numbers. There are other possibilities here, but there's our 3 numbers in that collection that adds up to a multiple of 6. Neat. Okay. So there's a fact that there's a new fact there about numbers that you may not have, or collections of numbers there, right, that you may not have been aware of. Okay, I'm going to pause here for a moment, and then we're going to look at another kind of similar example application of the pigeonhole principle. Okay, so let's look at another problem now, another application of the pigeonhole principle, kind of similar to that last example. So in this example, oh, by the way, now most of these examples, not all of them, but most of these examples are from the book Discussion of the Pigeonhole Principle, and that's easy to find. That's the beginning of chapter 3. So that would be pages in the book 69 to, I'm thumbing through the book here, through about 73, okay? I think all these examples are in that section of the book. All right, so so in this example, in this problem, a chess grandmaster, we're told, has 11 weeks to prepare for a tournament. So in order to prepare for the tournament, he's going to, of course, play games, right? And so chess games. So so his plan is to play one game, at least one game each day. But then he doesn't want to exhaust his creativity there, right? So he doesn't want to play more than 12 games in a week. All right. So all right, so one game, so for this 11 weeks, right, at least one game a day, but no more than 12 games in any given week. So what we want to show then is that there's a sequence of consecutive days, where the grandmaster will have played exactly 21 games, okay? So, so in some of these, in some sequence of consecutive days in these 11 weeks, we know that he will have played on that sequence of days exactly 21 games. All right. So let me show you how we can use the pigeonhole principle to solve this problem. So I'm going to make partial sums very similar to the prior example. So let's let A1 be all games played on the first day. Okay, well, of course, that's just the games played on the first day, right? So all games played on first day, and then, but we're going to continue with this pattern. So we're going to let A sub 2 be all the games played on the first 2 days, and then. Actually, let me capitalize these things, because these are partial sums, right? So, A sub 1, right? Capital A sub 1. A sub 2 is all the games played on the first couple of days, right? And then A sub 3 would be all the games played on the first 3 days, and so forth. All right. So so again, these capital A's are sorts of partial sums, right? They're partial sums of games played on a sequence of consecutive days from the beginning, right? So we continue building these partial sums until we get to the last day, and so he's practicing for 11 weeks before this tournament. So there's 77 days, right, in which he can play games. So finally, capital A sub 77 there would actually be all games played, right, on the first 77 days, or that's actually on the all 11 weeks, right? So that's the total number actually of games that he is going to play, right? This last partial sum, A sub 77. So I want to point out here now that what we know about these numbers A sub 1 through A sub 77, right? First, all of them have to be bigger than or equal to 1, right? So because he's going to play a game every day, right? And so and we know that these partial sums are actually increasing, right? We know that they're going up, right, from one partial sum to the next, because he's going to play at least one game each day, right? So A sub 2, the number of games he plays on the first 2 days, has to be more than the number that he played on the first day, right? And then A sub 3 has to be more, the number of games he plays on the first 3 days, right, has to be more than the number of games he played on the first 2 days, right? And that has to be more than the number of games he played on the first day, because he's playing a game, right, at least one game every day, all the way up to this partial sum A sub 77, right? Okay, and this we know has to be less than or equal to the total possible number of games he would play. And remember, he wasn't going to play more than 12 games a week, right? And this is for 11 weeks, because he's got 11 weeks to practice. So you know that capital A sub 77, that total number of games that he plays, is less than or equal to, it doesn't really have to be equal to, but it's less than or equal to 132, right? Okay. All right. Now here's the trick that that makes it possible for us to make this conclusion that there was a sequence of consecutive days in which he played exactly 21 games. Because here's what I'm going to do. I'm now going to go back and I'm going to form some new sums. I'm going to take A sub 1 and I'm going to add to that 21, okay? So I'm going to take A sub 1 and I'm going to add to that 21, and I'm going to do that, add the same number 21, which is the, remember that's the, what I wanted to prove was that there was some sequence of days in which he played 21 games. So I'm going to take that 21 and I'm going to add it to all of my partial sums here, right, all the way up to the last one, right, which remember is A sub, I'm calling that A sub 77. That was the total number of games played on all 77 days, right, of the 11 weeks. So you get it. We're going to get another a collection of 77 numbers here, which are these 77 partial sums, all with 21 added to them. And I want to point out we know something about these numbers as well, right? Again, they're always increasing, right? A sub 1 plus 21 has to be less than, this is A sub 2 plus 21, right? Has to be less than A sub 2 plus 21, right? And it has to be less than A sub 3 plus 21, and so on and so forth to A sub 77 plus 21. This has to be greater than or equal to 22. A sub 1 plus 21 has to be greater than or equal to 22, because A1 is greater than or equal to 1. And this quantity, A sub 77 plus 21, has to be less than or equal to 153, right? Which is the 132 plus 21 added to it, right? See, we know a sub 77 is less than or equal to 132, so a sub 77 plus 21 is less than or equal to 132 plus 21, which is 153. So if you look at what we've done here is we formed a bunch of numbers, right? A1, A2, A3, that's a group of 77 numbers, and now we have A1 plus 21, A2 plus 21, A3 plus 21, up to a sub 77 plus 21. So there's another 77 numbers that we formed. So altogether, notice we have 154. This big collection of numbers, that's 154 different numbers, right? You have 154 different numbers there, right? And notice they're all different from one another, correct? Okay, because this group of numbers is always increasing. Of course, this is going to be, and this group of numbers, right, is also all different from one another, right? Okay, so so we've got there. This is 77 completely different numbers, and this is another 77 completely different numbers here, right? But altogether, 154 different values, all between 1 and 153. So notice the pigeonhole principle now has come into effect, right? Okay, because you've got 154 numbers, but all these numbers are between 1 and 153. So that means 2 of the 154 different numbers have to be alike, right? Okay, correct. Okay, so 2 of them have to be the same because you've got 154 different ones, but they're all between 1 and 153. So 2 of them are alike, but it can't be 2 numbers in this list, right? Because those numbers are all increasing. So you can't have 2 numbers in this first list, this top line, the same, and you can't have 2 numbers in the bottom line the same, right? Because these numbers are also always increasing. So that means the 2 numbers that are the same, one of them has to come from this first collection, right? And one of them has to come from the second collection, right? So let me write down the 2 that are the same, right? I don't exactly know what their subscripts are, but so you have a number here in the first list. Call that a sub I, right? Okay, and right? Okay, so and that must be the same as one of these numbers in the second list, right? But these are all of the form, one of your partial sums. I don't know which one. I'll call it a sub j plus there a 21, right? Okay. So that's interesting, right? So we've got 2 values that are equal of this form, right? So I think that actually now gives me my conclusion, right? Okay, because look, a sub I. What? This partial sum has to be this partial sum has to be. This subscript has to be less than this one, because what you're saying is if I take this partial sum, that's the number played to day j, right, or the first j days, and I add 21 to that, right, that would give me the number of games played in the first I days, right? Correct? So the number of games played in the first j days, if I add 21 to that, that gives me the number of games played in the first I days, right? So that means then that the number of games played between day j up to day I has to be exactly 21. Does that reasoning make sense to y'all, right? Okay. All right, so let's repeat what this is saying, right? So the number of games played up until day J, right? If I add 21 to that, that has to give me the number of games played up into in the first I days, right? Okay, so number of games played in the first J days plus 21, that has to give me the number of games played in the first I days. So I think that means that the number of games played between day J and day I has got to be exactly 21. I think that's what we were trying to prove, right? Up to day I equals 21, and that's exactly what we were trying to show, right? Okay, there was a sequence of days in which he played exactly 21 games, right? So it was after after the Jth day, right? Starting on the J plus 1 day up to day I. Okay, so say that another way, from day J plus 1, right, up to day I, he played 21 games. I shouldn't assume it was a he, right? Okay, so the Grandmaster played 21 games. Okay, I've got one last, so that's again kind of a curiosity there, all right. I have one last example to show you, and this one actually is a lot more relevant. Let me see where our time is here, though, so I don't run us out of time, okay, as I'm frequently want to do, right? Let's see if I can get the recording app here to respond. There it is. Okay, so okay. Oh, right. So we've got some time here to show this last example. All right. So again, so here's an application of the Pigeonhole Principle that shows up more in practice. Let's show that, so here's something that you know from elementary school, but let's see why that's true, because it just comes from the Pigeonhole Principle. So suppose you have a rational number, so that's the quotient of two integers, right? The quotient of two integers. Let's assume that they're positive integers, although we can easily adjust the argument if one of them or both of them are negative. So let's suppose we have the quotient of two integers, and of course, when you, if you want to, you can take the quotient of two integers, right, and you can, instead of writing them as the quotient of two integers, you can write them in decimal terms, correct? The problem with sometimes, of course, writing the quotient of two integers in decimal terms, though, is sometimes you will get a repeating decimal, correct, right? And if the decimal is repeating and non-terminating, then that's kind of messy, right? So because you get this infinite decimal expansion, okay? But actually, what this theorem shows is that anytime you take a rational number and you write down its decimal expansion, you always will get a repeating decimal. Now, that the decimal that repeats might be 0, right? Okay, in which case you have a terminating decimal expansion. But of course, sometimes you get a non-terminating decimal expansion that repeats, right? Okay, that's another possibility. And again, what we want to show here is that's always going to be the case, right? When you take the quotient of two integers, you will always get, in its decimal expansion, a repeating decimal, right? So, for example, if we just look at the quotient of two integers, 17 over 44, right? Okay, then you get 0.38636363, right? So that, notice that sequence 63, right? Repeats, right, to form the entire decimal expansion of the number. Of course, it is possible to write down non-repeating, non-terminating decimals, right, okay, and those are perfectly good numbers, except those are not going to be rational numbers, all right? So whenever you have a non-repeating, non-terminating decimal, you cannot write that as the quotient of two integers. That's not a rational number. So it's a perfectly real number, but it's not a rational number. All right, so let's see, why is it that when we form the decimal expansion of a rational number, we always end up getting a repeating decimal? And again, the repeating part might be 0 repeating, in which case we say the decimal expansion terminates, right? All right, so, well, it's as easy to understand, right? Let's think about how we actually form the decimal expansion of a rational number, right? So you can do that. One way of doing that, of course, is to use long division, right? So you can take your denominator, correct, and you can divide that into your numerator, right? So you can write your denominator as the, in this long division process, this quantity that we call the divisor, right? And then we can write the numerator as, in this long division process, the quantity that we call the dividend, correct, right? So we're going to take the divisor and divide it into the dividend. Now, how does this long division process work? Look, there are plenty of algorithms for doing long division, but the usual one that you're taught in grade school, in the United States at least, looks something like this, right? So, you take, by some process, right, you take the divisor and you divide it into the dividend, and then that generates a digit, right, in your quotient, correct? And just one digit in the quotient, right? And then you take your that digit in the quotient, you multiply it back by the divisor, right? And then you somehow subtract that from your dividend, and you end up with a remainder. Okay, that's what I wanted to get at here, is you're going to end up here with a remainder, and then you repeat the process, correct? So you take your divisor again, and now you divide it into the remainder in some way, right? And that generates the second digit in your quotient, correct? Okay, and then you continue this process, right? So you multiply this digit back through your divisor, and then you compute your next remainder, correct? Okay. And then divide your divisor into your remainder, and that generates the next digit in your quotient, right? So this is this sort of continuing process, right, that you use to generate, that you can use, right, to generate the decimal expansion of a rational number. Now, what's important here, though, to remember is that when you generate these remainders, right, all these remainders, they must be always not 0, okay, right? Okay, so they're going to be bigger than or equal to 1. If they're 0, then this process terminates, correct? And then you have a terminating decimal, right? But if the remainder is not 0, correct, then it's always got to be between 1 and the divisor minus 1, right? So you cannot ever have your remainder as large as your divisor, right? Okay. So again, I'm not writing down all the steps of this process, correct? Okay, but you've done this plenty of times in grade school, correct? So you know how this process works, right? And so you just keep generating, as part of this long division process, right? You just keep generating these remainders, correct? And these remainders are always between 1 and 1 less than your divisor, right? Well, look, after you've generated a lot of these remainders, right, okay, what inevitably must be the case, okay, since the remainders are all between 1 and n minus 1, and you're going to generate arbitrarily many of these remainders unless one of them turns out to be 0, in which case the process stops, right? But if they don't, one of them doesn't turn out to be 0 and the process doesn't stop, you're going to generate an arbitrary number or an indefinite number of these remainders. So by the pigeonhole principle, right, what's got to happen? You've got to have a remainder that recurs, right? So you must have one of these remainders that repeats itself. But of course, once a remainder repeats itself, what's going to happen in your decimal expansion? Then the decimal expansion, right, is going to start repeating, because once a remainder repeats itself, right, then you're going to be just going through the same sequence of remainders, right, again, when you're because you're always dividing the same divisor into these remainders, correct? So as soon as you get a repeated remainder, that means this sequence of digits in your quotient is also going to start repeating, right? So that's it, right? That's why the decimal expansion of a rational number has to eventually repeat, right? Because at some point, one of these remainders in the long division process would have to repeat, and that's by the pigeonhole principle, right? Okay, because there's the limit on the size of these remainders. Okay, well, that's where we're not going to get into Ramsay theory, I guess, then today, because we're going to run out of time. And so we're going to take up Ramsay theory next time. So that's a really interesting and fun topic. And I don't think that will take us the whole lecture to talk about Ramsay theory, although it is, again, a fun topic. And then we'll get into our next subject, which I think is going to be, we need to revisit, I've been promising this since almost the beginning of the course, right? We need to revisit inclusion, exclusion. So, which is one of our fundamental counting principles. So we're going to revisit that and look at the full version of inclusion, exclusion, right? And inclusion-exclusion theorem, remember, that is useful in helping us count the union of sets, okay, which is sometimes it's frequently a tricky process if the sets are not disjoint. If the sets are disjoint, it's easy, but if the sets are not disjoint, it's not easy, and that's where inclusion-exclusion becomes helpful to us. Okay, all right, so we're through with our lecture here for Monday, March the 30th, right? So I will see you again on, what is that going to be, April 1st? Oh, April Fool's Day. That's a great day to talk about Ramsay theory, okay, and inclusion, exclusion as well. All right, so see you guys then. Stay safe until then.